Uh, so the talk of today, I was planning to make it to focus more on the intuition behind some of the analytic techniques that I use or that are used to study determinant or index on manifold or that are singular. So, maybe as a motivation, it probably a bit elementary, but just to recall why one would like to understand well the heat kernel on a singular space or even just on a manifold. So yesterday Andrew mentioned the famous Raysinger determinant of the Laplacian and how to define it using the zeta function. So the determinant define it to be the exponential of minus the zeta function of the derivative at 0 of the zeta function of the Laplacian. So here I can think of the Laplacian on some compact manifold for the moment. And the zeta function S you define to be the sum of the eigenvalue. So where where this is the spectrum of the Laplacian for some metric G metric for which we can define the Laplacian, and this sum will converge for real S big enough. In fact, for real S larger than n over 2, where n is the dimension of the manifold. And one nice way to see it, probably many of you have seen it or are very familiar with this, but I just want to repeat it again because this sort of idea is useful in more complicated situation as well, is to see where how to extend this function. So it's holomorphic when S is big enough, the sum will converge and there's no problem. But to define it at 0, we need to extend the function meromorphically, and it implies we have to know where are the poles. And one nice way to find where are the poles is using the heat kernel. Or the trace of the heat kernel. So let e to the minus t be the heat kernel of delta. And so for t positive, that's a smoothing operator. In particular, it will be trace class. So you can take the trace and as t goes to 0, it's singular, and it has a sort of a Taylor series in t with these coefficients. And the important feature is that you can also think of it as in terms of the eigenvalues. Yes, it's I goes from 0 to infinity of e to the minus t lambda I. And using this formula, if you can rewrite the zeta function in terms of the heat kernel. So you can write the zeta function of the Laplacian as 1 over, and then the trace of the heat kernel. And I will subtract 1 because I don't want to have the 0 mode. And then I integrate in t. So when I subtract the 0 mode, that ensures that as t goes to infinity, it decays very fast at infinity. So the integral will converge if s is big enough. Okay. And so from this point of view, understanding where is the functional morphic is understanding the behavior of the heat kernel for short time. Okay, so for large time, the integral will converge no matter what is s, so that will be holomorphic. And the issue is for integral near 0, the integral may diverge if s is not, or the real part of s is not sufficiently big. And when you know that the heat kernel, or whether its trace, has a short time asymptotic, you can use it to find exactly where are the poles. Okay, so we can use the short time asymptotic of the trace of the heat kernel to extend the zeta function meromorphically and find where are the poles. Okay, so you see that the most probabilistic term is the first one, so it goes like 1 over t to the n as t goes to 0, and so that tells you when it fails to be integrable. But as to increase s, the power of s, the power of t in the expression as t approaches 0, you can remove singular terms step by step, and each time you make the trace minus some of the term decaying more and more in t, so that will make the zone or the region where it's holomorphic bigger. But the cost is that you have to, when you subtract it, you have to add it back. But the point is that for this term, you can compute explicitly what's the integral, and you can see that it's meromorphic with a specific pole. Okay. So if you compute, so 1 over gamma s, so I'll restrict just the integral from 0 to 1, because integral for large t doesn't really affect the result. And if you have a term of this form, t to k dt, you can just integrate. And so what one gets is 1 over, well, let's just do it, t to the s plus k over, well, I forget to subtract the n over 2. Okay, and we have to take it between 0 and 1. So what we get is 1 over gamma s, and then s, this is the ak, and then ks minus n over 2 minus k. So what we see is that hence the coefficient ak gives a pole at s is equal to n over 2 minus k. Okay. So there's what is important in the definition of the determinant is that we need to know the function is regular at 0. So here, k is an integer, so we get poles. So this gives poles at n over 2, n over 2 minus 1, etc. But there is no pole at s equal to 0, and the easy way to see it is that the 1 over the gamma function has a 0 at s equal to 0. Okay, so sorry? Mm-hmm.
The poles are cancelled by the zeros of the gamma function.
Real back to what we actually do there.
Yeah, some poles do exist, but until zero,
Okay.
then there are no more.
Okay.
Never mind.
Yeah. Yeah, so to be safe, we say that, let's say that there might be a pole. Yeah. And what is the worst that can happen is that there's a simple pole at these places, and there are no pole at s equals 0. So since 1 over gamma s is s plus, so it vanishes at s equal to 0. There is no pole at s is equal to 0. Okay. So, well, I just wanted to recall one of the use of the heat kernel in this sort of thing. And so, before attacking the case of a singular or surface with cusp, I would like to briefly recall a strategy to construct the heat kernel due to Richard Melrose. Okay, so okay. So on Rn with the standard metric, so the heat kernel is given by denoted by k, so it's 1 over then the exponential of okay, so just to be sure I'm not writing something silly, yeah, something of the sort. So well, using Fourier transform, there's a nice way to find this heat kernel. And it's quite important. It's basically the starting point if one wants to construct the heat kernel on a general compact manifold. Well, Rn is not compact, but it's the local model for any manifold. And intuitively speaking, when you think of the heat kernel as solving the heat equation, you imagine that when not a lot of time elapsed and the distance between x and x prime is not too big, you don't really see the geometry of the manifold, or you can approximate it by the Euclidean metric nearby, and
Square, I think.
huh?
You need a square distance.
Oh, yeah, square, yeah. Thank you. Okay, so I did write something. Okay, so, well, in any case, so that's the starting point, in a way. And to construct the heat kernel on a compact manifold, the approach is usually that you start with using the Euclidean heat kernel to build an approximation to the heat kernel, and then you try to refine your approximation, make it better and better to ultimately obtain the heat kernel. And one geometric to one geometric construction of the heat kernel following Melrose. So one way to implement this geometrically is to try to identify a space where this would become smooth. So if you see as t approaches 0, it's become singular somehow. But if x and x prime are different, then because of the minus sign, as t goes to 0, this approaches 0 exponentially fast, so that would cancel the decay there. So if t goes to 0, but you are away from the diagonal, that will be smooth, and in fact it will approach 0 really fast. But on the other hand, if x and x prime are equal, so if you lie on the diagonal, then this will be 1, and so that will not cancel for the singularity over there. So it will be singular near the diagonal, and it turns out that the appropriate space where you can resolve to think of this as a smooth function somehow is to blow up the diagonal at time 0. So you consider the following heat space, so x to h. So that's x squared, so the manifold cross r plus, and I'll use instead of t, I'll use square root of t. So square root of t will be better variable to study the heat kernel. And then what I do is I blow up the diagonal at time 0. So here the picture is the following. So let's see, you have a square root of t, and then you have x squared, and let's say that this dotted line here, it's the diagonal. And what I do is I blow up, not in the sense of algebraic geometry, or well, of course, because there's no complex structure, or not a real blow up. So it's not it's blow up in the sense of introducing polar coordinates. So when you blow up, that will look like this. So you introduce new coordinates so that you keep track of the direction from where you approach the diagonal. Okay, so that's a sort of a semicircle like this. And so you have the whole phase, so that's the temporal boundary. So when you blow up, you keep these faces. But there's a new one that called the temporal phase, and that's basically where things will be of interest. So I think of this as a blow-down map. And so basically this construction, this amounts to introduce new coordinates near the diagonal at time 0. So, namely, you look at the distance from the diagonal. So I put t plus x minus x prime, and then I use angular variable, so omega given by omega naught and omega prime, so with the property that square root of t is equal to r times omega naught, and x minus x prime is equal to r times omega prime. Okay, and of course, there's you can use locally the order coordinate x plus x prime. So there's one missing direction, but I'm just using the coordinate in that direction. But we don't need to change the other coordinates. And well, we can see what happened to this each kernel if x happened to be Rn, and we do the change of coordinates. So when x is Rn, we get that k can be just rewritten as 1 over 4 pi n over 2, and square root of t because Rn omega naught n, and then the exponential become omega prime square over 4 omega naught square. So in this case, maybe I can put the Rn outside, and then put so here 1 over So it's still singular as one approach this new phase. Each kernel is singular, but it has anyway it's a singularity that is very well described in this setting. It's just we precisely describe how it blows up at this phase, and then the remaining part is a smooth function on the total space. Okay. So in this case, if this is smooth on on that phase, and now when we approach the boundary of the phase, so that means that omega naught is going to 0. The omega prime has to stay omega prime square has to stay positive when we approach the boundary. And so so this function, which is really defined also on the space, as we approach the space, the end of the phase, it vanishes to all order at this boundary here and there. So in fact, this function inside vanishes to all order at the temporal boundary. So this phase and this phase. And here, well, it's singular, but it's approaching singular to power r to the minus n. Yeah.
What's the fiber data of the timeline? What's the fiber data?
The fiber. It's so it's an isomorphism everywhere except the diagonal. It's this phase. It's just it's well on the picture it's looked like a semicircle, but no. But it's just a problem with the picture. I cannot draw in higher dimension. So it's yeah. So that's the coordinates that describe the position there, and that's Sn. Sn, but in fact it's half a sphere. And then there's the other coordinates x plus x prime that tells you where you are on the line. So the yeah, it's only at t equal to 0 that we blow up. Yeah. So we get half a sphere, but times the diagonal. So it's the diagonal. So the base is the diagonal, and then the fiber are half sphere. But in this this picture where there's just one variable, it's a semicircle. Okay, so if there's just one space variable, it's just really a semicircle. And so in fact, we can describe it so as saying that we see that if I multiply the heat kernel, in this case by Rn, so to remove this part, this singular part, then that becomes a smooth function on that on that space. So it's really it's I pull back my heat kernel that I think of leaving there. I pull it back here, and then it becomes smooth at the cost of multiplying by r to the power n. But in fact, more is true in this notation. So the dot here means that it will vanish to all order at the phase TB. So the temporal boundary phase, the function is smooth up to the boundary, and it vanishes as well as all its derivative on this phase. So the only part where it's non-trivial, it's on that phase, where it has a Taylor series. So and vanishes with so the notation, the dot with the TB, means that it vanishes with all derivative at the phase TB. Okay, so that's for the Euclidean space. And in fact, one important thing to notice, is that since the normal bundle of the diagonal is just the tangent bundle, the interior, so you can think of this new phase introduced here as a compactification of the tangent bundle in a canonical way. And so if you remove the boundary of this new phase, so if you look at the interior of it, it's identified with the tangent bundle of the manifold. Okay. And so I said half sphere, or you can think of the fiber as just ball, dimension n. And so the ansatz to build the yield kernel when on a compact manifold with this approach is if X is a compact manifold with Riemannian metric G, then then the E kernel times Rn will also be an element will satisfy the same property. Okay, so that provided I multiply by this boundary defining function for this new phase, it becomes smooth, and moreover, it vanishes to all order at this temporal boundary. Okay, so you start with this assumption that the heat kernel satisfies this, and then to show that it's actually true, so that the heat kernel indeed is in that space, you slowly build an approximation to it. Maybe I'll keep the picture here. Okay. And the way you can see that the Euclidean heat kernel approximates the heat kernel in that case is restricting to this boundary phase essentially correspond to restricting to the Euclidean setting. So so the map which to the heat kernel associated is restriction to the temporal boundary phase should be seen as a symbol map. So when you look at the maybe really to restrict, I have to multiply by Rn. So then it becomes smooth. So I take the most singular term at this phase, and then the claim is that this most singular term is should be somehow the heat kernel of the Euclidean space, or more specifically in each fiber. So each fiber is just the Euclidean space, or a compactification of it. So in the interior, so each fiber is just the Euclidean space in a way. It should be the Euclidean heat kernel, but of course on that space there's no time, so time you have to go up in the picture. So it's sort of the frozen heat kernel. So when you look at your heat kernel and then you approach that phase, you rescale in a situation where x becomes, the distance between x and x prime becomes smaller and smaller, and the time also becomes smaller and smaller proportionally. And in the limit, what you obtain, it's supposed to froze on the Euclidean heat kernel. So, and well, I don't want, or in fact, I cannot make it more precise for the lecture, but basically, so if K is the heat kernel, so if we assume that this heat kernel exists on that space, then in fact you can check that the symbol map, so the restriction to this phase should be the frozen Euclidean heat kernel. So then should be the frozen, so in the sense that there's no notion of time, a frozen Euclidean heat kernel. So in the picture I've factored out the Rn, but otherwise what was left is this 4 pi over, in the Euclidean case, 4 pi n over 2 omega 0 n, and then there was the exponential of omega gram square over 4 omega 0. I think that's correct. And the only thing you need is to say what's the square in this case. So so you have to replace by the length of omega prime. So you can think of it as a tangent vector on Tx, and then you can put the, I'm a bit sloppy, but you can think of using the metric to fiber-wise define what's the square, or the inner product of omega prime with itself. And so basically that's supposed to be the model, the top order term. And then if you look at the next term in the Taylor series, this front space, it's a correction due to the fact that we are not on the Euclidean space, that the geometry pops out as time evolves. So then what you can do is proceeding recursively, one can find the full Taylor series of Rn at this temporal phase, providing we assume that it's a solution, or that's the heat kernel. Okay. So we don't know yet that the heat kernel exists, but we know that if it exists, the Taylor series has to be given by us, something that we can actually compute. And then the strategy in the construction of manifolds point of view is that then what you can do is take K, an element of that space, so of 1 over Rn, C dot with such a Taylor series. So any function, so this exists, no matter what Taylor series you have, you get a function smooth whose Taylor series will be given by that. So it's using a Borel lemma. But when you do this, that's just an approximation to the solution. So it's solved to all order as t approaches 0, but otherwise it's not the solution. Okay. But so this is the heat kernel, but modulo nice error term. So in other words, the main difficulty of solving the heat equation all happen at this phase. So when you find the Taylor series, basically you win. So you can just take any function that will approximate this heat kernel, and then it will solve the heat equation modulo an error term. But this error term will be nice, and then it's sort of easy at that stage to just get rid of it in a relatively easy way. Okay, so well, I apologize a bit if it's just review of things that are very well known, but the advantage of this point of view is that you can apply a similar method to construct the heat kernel on certain singular spaces. Okay, so once you have this construction, so you know that you have a Taylor series at this front face, and then from this, I should say, once we know that K is actually in this space, then the short time asymptotic expansion for Louisiana. So the heat kernel at T of trace of yes.
Order of I, n or minus n? We belong to.
Oh yeah, minus n.
So this construction has nothing to do by to assume that n is compact. Even n is just a manifold. You can still do that. Not even completely.
Yeah, well, in principle, but as you'll see, it can get more complicated. So what I want to do now is do the case of a Riemann surface with cusp. So that's a situation where it's not compact. But to really have a nice asymptotic expansion for the trace, you need to understand what's happening at infinity. And so that means you have to blow up a bit more.
But
typically.
for the non-compact manifold, the heat kernel is not
Mhm.
same Laplacian operator.
Uh-huh.
So which one you use in your kernel construction?
Mm,
You have some complete manifold.
yeah, yeah, yeah,
It needs a homotopy.
yeah.
You didn't say on what manifolds to work.
Yeah. Well, so well, let me describe what for what sort of manifold I want to apply. It's not. I'm not claiming that's a universal construction that works all the time and that makes everybody happy. Sometimes it fails, or sometimes it requires adjustment. But it's a principle that, nevertheless, can be applied in a wide variety of situations. So. And so each kernel on Riemann surfaces with cusp. So that's the situation I want to consider. So let's imagine be. So I'll assume it's hyperbolic, but it's not really necessary for the assumption. So let be hyperbolic Riemann surface with, let's say, one cusp. Okay, so here's a picture. So put one cups, but you could put more than one, and then you could change the metric in the interior, but you want the behavior here for what I want to do. I want the behavior to look like a cusp here. So, and what does it mean to look like a cusp? So near infinity, so near the cusp, the metric is given by d rho square over rho square plus rho square d theta square. So and so here theta, I think of it as a variable on the circle, and the infinity is when rho goes to 0. Okay, so I have my coordinates rho that is 0 at the tip of the cusp, and then positive in the interior, and then the theta variable is the variable around the cusp. And so that's one way to describe it. And for the construction, it's useful to, in fact, blow up, in a way, blow up the cusp. So if I compactify my Riemann surface to put a point at the tip of the cusp to get a compact Riemann surface, I can then blow up the surface, and what I get, but blow up in the sense I described it earlier on, in the sense of introducing polar coordinates. So I put a boundary at infinity. So the metric is only defined in the interior of this Riemann surface boundary. It doesn't extend to the boundary, because when you put rho is equal to 0, that expression doesn't make sense. But the boundary is nevertheless very useful to encode information about the asymptotic behavior of the metric or of the Laplacian at infinity. And so what I want to describe now is the construction of Vaillant for the heat kernel. So the heat kernel, and maybe I'll call this new surface sigma tilde, the one with the boundary. So the heat kernel in such a context was constructed by using the approach of Melrose. So Vaillant was a student of Miller and Melrose, and well, the heat kernel in this context was studied by many people before Vaillant, but here it's an approach using the construction I just outlined that is very powerful, in fact, because you get to understand the heat kernel very well. Although it gets a bit technical to some extent. So it goes as follow. So one need NANSAT, or that is a heat space where the heat kernel will be smooth. Okay, so yes, in this approach of Melrose, the principle is that if you study a singular function or a singular object, then it's easier to understand it if you can resolve the space or describe it on a space where it becomes smooth, because smooth functions are well known, well understood. So as soon as you get the proper space where it becomes smooth, then you can apply all the things you know about smooth function to understand the singular object. Okay, and well, I'll draw a picture of this space. In this case, so I'll forget about the variable theta, because in this heat space I can only draw 3 dimensions, sort of. So, but the theta variable is supposed to be in the picture, and so I start with the same thing. So I have my boundary defining function rho, and rho prime for the other coordinates. So this plane here, that will be x square or x tilde square. So I work with this Riemann surface with or this surface with boundary, and so here's the diagonal. And in the previous construction, what we did is we were blowing up the diagonal, because the heat kernel, the analogy that the Euclidean heat kernel will approximate well the heat kernel for short time and short distance works, except when you approach the cusp. So the metric is complete, but the area is finite. But when you approach the cusp, the circle direction just collapse. So when you have to blow up, you need to take into account the situation that when you have short time, this distance still should rescale at the same time. It should this collapsing should be taken into account. And moreover, for technical reason, or when you want to blow up, so that's a manifold with corner here, because really it's a manifold with only times itself and then times another one. So there's really a corner here. It's two distinct variables. So here it's the plane is x tilde times x tilde. So I take rho to be the boundary defining function for one, and then rho prime will be the boundary defining function for the other one. Okay. And then there's also the theta variable that I cannot draw. So the correct way to blow up is well, you cannot just blow up first this diagonal here because it's end in a corner in the middle. So that will give something not very elegant, hard to understand. It wouldn't help. So you need to first blow up two other things before you get to blow up what you want to blow up, namely this diagonal. And so one first blow up, so the each space one consider one first blow up this corner at all time. So it's d sigma tilde times d sigma tilde, and then for all time. So when I do this, that's what I get. Sigma tilde, yeah, oh, sorry, x is, sorry. Yeah, so there's no x, it's sigma. Maybe I guess you can put a tilde or not a tilde. It's you choose what's the better notation. But okay, so that's supposed to be the each space. And then what we blow up, so there's the diagonal, and we can lift it to this space, and then it will meet this new face that has been blown up at one point here. So what we can do is blow up that point first. Okay. So that will that new face will encode what's happening at the cusp somehow. Okay. So the second blow up is you blow up the diagonal in sigma tilde. Well, I don't have a quick, elegant way to write it, but it's the diagonal, and then at time 0, and then you intersect with this new face here. This new face, so it's when rho prime are equal to 0. So you lift the diagonal, and then it will meet this face at one point, and then you blow up that point. And then finally, the last blow up is you blow up the diagonal. So this face, we can call it the boundary face. This face, the cusp face, and then this face, the temporal face. And then all the rest is other face, but nothing will happen. So the principle is that in this construction is that all this face that had been blown up, something will happen at this face. So the E kernel will have a non-trivial asymptotic expansion at each of these faces, and everywhere else it will approach 0 very quickly. And well, it's a delicate construction, but I just want to give you the intuition of what's going on at each faces. What's the model at each faces? So, and maybe I should say also that the construction of variant is quite general. It's not just for surface; it's for manifold of arbitrary dimension, and it's not just for cusp. More generally, it's for fiber cusp. But I just focus on this the simplest possible situation when there's a cusp involved. Okay, so at the temporal boundary face, so as before, the model is the Euclidean E-kernel. So at the cos phase, so that's what the new thing that is happening somehow. So intuitively, this blow-up that I did, maybe I should just redraw the picture. So the blow-up that I did of introducing a circle at infinity, it's from a geometric point of view, or from the point of view of the heat equation, it's not so natural because it's really collapsed at infinity. Okay. And so when you have heat in the cusp, you don't expect the heat to see a circle there because it's really just a point. Okay. So if you so what happened here at this phase is that you should think of it as having the heat diffuse instantaneously in the cusp. Okay, so in this artificial circle, immediately at time 0, so this blob was at time 0, the heat diffused in the cusp. Okay, so, and the model there is basically the heat kernel of the Laplacian on the circle. Okay, so at the cusp, you are on the boundary, you have a circle, and what's happened here is that you have the heat in the circle that maybe you could start with something artificially distribute there, but since geometrically it's really a cusp, what happened with this heat kernel or with the heat equation is that the heat will diffuse instantaneously in the cusp, and so it's at time 0. So in principle, you think there's no notion of time, but at this phase, there's a notion of renormalized time somehow, a time that also involves the space in the cusp direction. So really, you can think of it as the heat evolving on that phase. So starting with the initial value is at that phase, and then the variable that parameterizes the phase in that direction, you can think of it as some sort of renormalized time. And at the other phase, you could think of it as the result of the heat completely diffuse in the circle at infinity. So it becomes constant, it becomes, if you start with the distribution of heat, it becomes constant on the circle at infinity. But in this picture, it happened instantaneously with respect to the notion of time. Okay. And so for the Laplacian on the circle, the kernel is constant function. So it means that for the heat kernel, as it approaches the end of the phase, it becomes constant. So at this stage, it becomes completely constant at the boundary. And so the last phase at the boundary phase, so it's a situation where it takes into account what's happening in the cusp, but it's a situation where really the heat is completely distributed on the circle. So you can't really think of it as living on the cusp somehow. So what is left is, so in this case, the kernel is just finite. Well, it's just one-dimensional in this case. So on that phase, you'll have the model. So the top order term will be the heat kernel, but for a matrix. Instead of being a differential operator, that will be the heat kernel of a matrix. In fact, just this will be the heat kernel of a matrix of a matrix. So somehow you just scale the direction in the circle, and you're left with just a constant. So in this case, the heat kernel is easy to understand. And okay, so that's basically the tree model. And then I'm hiding a lot of detail, but the idea is that you have this model at each of these phases, and if you have a heat kernel that really is the heat kernel living on that space, they have to come from this different model. And then what you can do is find what should be the Taylor series at each of these phases, provided you have a solution. Once you find the respective Taylor series at each phase, you can just take an approximate heat kernel with this Taylor series, and then the same story happen, namely that you have a very good approximation of the heat kernel. The error term, you can get rid of it relatively easily, and then you you actually get the heat kernel on that space.
But why, when you say when it approaches cusp, the heat kernel goes to a constant? That's what you say. The heat kernel goes to a constant. When X or Y.
It becomes projection onto the constant function. So if you have on a compact manifold or just on a circle, you have the heat kernel. What it does is it diffuses the heat, and then at infinity you expect that whatever you start as the distribution of the heat becomes constant at infinity. But in this picture for the cusp, when we think of it as a circle, a blob circle, this process happened, but with a renormalized notion of time. So it happens instantaneously at the beginning, but if you use a renormalized notion of time, you can think of it as just the usual heat kernel in the circle, where before the old story starts with the actual heat kernel, the heat has to first diffuse in the cusp. Yeah, so something like that. So, well, in fact, when you start here, what is left is just the projection onto the constant function. So you don't see, you only interact with a function that lies in the kernel of the operator on the circle.